welcome to the jungle. Thank you for joining. Once again, I'm your host, Gringo Kurt. If you've seen previous episodes, then you know that we've got a lot of history to learn, so I'll keep this intro short. This is the timeline. This is when the Earth and the Moon were formed. And this is where we left off. So, let's get into it. Now, as we return to the timeline of Earth's history, I'd like to mention a few other essential pieces of the Earthling puzzle. As you can see here, highlighted as the span of time from approximately 3.8 to 4 billion years ago, I've labeled this portion of the timeline earliest evidence of biotic nitrogen fixation. And during that same period, you can see that I've also added ribosomes. You can see that the last universal common ancestor has been placed at the end of this period. As I've already described the evolution of ribosomes in episode 1, we'll begin there. A very detailed article was published on October 26, 2022. The title is A Short Tale of the Origin of Proteins and Ribosome Evolution. This article contains an incredible wealth of information about our current state of ribosomal coevolutionary understandings. Now, if you're unfamiliar with ribosomes or peptides, please refer back to episode 1. Okay, now, to set this up, we need to connect the transcription factors and RNA polymers to the DNA. And now, as a refresher, here you can most simply understand why I describe ribosomes as 3D protein printers. So, the ribosome reads the generated mRNA strand and then prints the designated three-dimensional version of the protein. See? When put basically, it's that simple. Proteins are a large piece of the early Earthling puzzle. If you delve deeper into the subject, you'll learn that it's the importance of proteins that caused the existence of functional ribosomes to become such a crucial step towards the formation of life as we currently understand it to be. I'll go ahead and read the two congruent sentences that indicated where to place the ribosomes on our timeline. The article states, life started around 4 billion years ago, characterized by the coevolution between peptides, probably originated by wet and dry cycles, and RNA molecules, where the first proto-ribosome arose. There are several lines of evidence for the last universal common ancestor at around 3.8 billion years ago. So to bring clarity, we will return to the macroscale perspective provided by our timeline, and I'll add some unifying thoughts that seem relevant when understanding how these clues relate. Because of the Jack Hill's findings, we have evidence of Earthlings dating back to more than 4.1 billion years ago. Because of the microfossils from the Nuvvuagittu supercrustal belt, we are accumulating an archive of early Earthlings, ranging from 3.75 to 4.28 billion years ago. However, we cannot yet attach a scientific name to any specific species, and we cannot tell if their bodies were utilizing ribosomes. We are not wading deep into details here. Our evidence presently tells us about the type of Earthlings that existed then, and though it's an excellent start, there are still intricately detailed questions that scholars are focused on developing. That said, some percentage of Earthlings before 3.8 billion years ago logically had them. Whether the subjects that paleontologists are presently studying possessed no ribosomes, proto-ribosomes, or fully evolved ribosomes, they cannot yet say. Earthlings had previously acquired DNA and RNA, but from this point forward, all Earthlings also possessed fully evolved ribosomes. This is a thick article, but it's a fascinating subject, so a recommended read. Now let's touch upon the biotic nitrogen fixation sharing this section of the timeline. It's interesting to know that approximately 78% of the atmosphere that we breathe consists of nitrogen, but it wasn't always like this. So, how this ingredient came into such abundance is why nitrogen fixation deserves to be studied. Evidence reveals that our history depended on it. To get a more complete understanding of this, I recommend another published work titled Modern Analogs for Ammonia Flux, From Terrestrial Hydrothermal Features to the Archean Atmosphere. This article was published by Scientific Reports on January of 2024. The following quote was the cause for placing two significant markers on Earth's historical timeline. It reads something like this. The geological evidence and presence of positively charged nitrogen, bonded to 4 hydrogen atoms and enriched with phyllosilicates, suggests that nitrogen fixation caused by organisms had originally evolved as early as 3.8 to 3.95 billion years ago. Then, isotopic and genomic evidence also suggests that nitrogen fixation using molybdenum-based nitrogenase occurred as early as 3.2 billion years ago. To most, that sounded complicated, so let's attempt to simplify it a bit. Biological nitrogen fixation first evolved into existence between 3.8 to 3.95 billion years ago. And then by 3.2 billion years ago, it had evolved to more efficiently utilize molybdenum. The effects of this then began to profoundly affect Earth's atmospheric oxygen levels. Within our present-day environment, molybdenum-based nitrogenase is recognized for being the most responsible for nitrogen fixation, so this was a historically significant time for the world of Earthlings. For those who are unaware, molybdenum is sometimes referred to as Moly for short, and Mo for shorter. It's a unique elemental metal that's often confused for lead, though its toxicity levels are significantly lower. It possesses a high melting point, and it's very attracted to iron. When merely introducing oneself to this line of research, you'll quickly find that molybdenum is responsible for breaking down various amino acids within the cells of our bodies, which is evidence of how involved molybdenum has been throughout Earthling evolution. While attempting to not get too technical, it's a metal that's responsible for transforming Earth's nitrogen into various components that Earthlings have required since back in the early days, all the way through and up until the present. This line of questioning also focuses on the correlation between the amount of molybdenum in oceans and on land and the presence of oxygen. When molybdenum levels rise, historically, oxygen levels have risen as well. Moly is a crucial component that's been on our planet's surface since the latter portion of Earth's crustal formation. Before that, most molybdenum would have sunk into Earth's inner layers during the differentiation period. It's very important to note that the evidence of Earthlings that I've been describing likely could have never evolved into the earliest forms of Archaea, which later evolved into methanogen, if those that came before them never began fixating atmospheric nitrogen levels. The first bacteria, which were named Cyanobacteria, would not have evolved either. As we'll study in episode 3, if Archaea and bacteria never evolved, then we definitely wouldn't be us. And so, the evolution of these life forms are very important moments of the Earthling family photo album. Oh yes, and we cannot leave out sulfur-reducing bacteria. The reduction of atmospheric sulfur compounds paved the way for developing an environment suitable for life to evolve into oxygen-producing organisms. So again, these are historically significant events. And speaking of oxygen, those nitrogen fixers were also essential for the early microorganisms that had aerobic metabolisms. Why? Well, because nitrogen compounds are essential for the synthesis of biomolecules. Biomolecules support both their metabolic processes and growth. And as we've studied these incredible footprints of our past, we can better understand the resilience that the various forms of life needed to have before we could evolve into who we all have become. When we chronologically order the significantly historic moments of our past, it leads to only one result: the understanding of why things have become as they are. But for now, it's time to start bringing this second episode to a close. We planned on ending this episode with the first snowball Earth. Well, as you can see on our timeline, we've reached that point. During episode 3, we'll begin from there and continue forward through time until finally reaching the next couple of snowball Earths. It'll include some of the most essential moments of our Earthling history. Moments such as the Great Oxygenation Event and interesting recent developments involving the evolution of eukaryotes, which are the types of cells that all plants, animals, and fungi are made of.
As always, you'll find a chronological list of all the published articles referenced during the production of this episode, complete with direct links right here in the description section. This will make it easier for you to dive deeper into the details.
Alrighty, well, that's it for today. Thanks for watching. Also, please like and subscribe if you're interested in nature reality. Cheers.